All right, hello everybody. Um, let's finish up this set of notes that we started in class. Um, we are dealing with generating functions. If you remember on the previous page, we ended up having a generating function that looked like 1 over 1 minus x quantity squared. Um, we expanded that using Mathematica, and we saw that the coefficients of x to the n were n plus 1. And so let's talk about how we could figure that out. We could prove that it's equal to n plus 1 using various of our tools that we have available to us. Okay, so we're going to start first with the series that we know. When we see something that looks like 1 over 1 minus x, we should immediately think, oh, that's a geometric series. That's things that look like 1 plus x squared plus x cubed plus dot dot dot. And so the coefficient of x to the n, or x to the k, is always equal to 1. So when you don't see a coefficient, you should always say, oh, the coefficient is equal to 1. So what this is saying is that the coefficient of x to the k of 1 over 1 minus x is equal to 1. That would be the shorthand for what this expression tells us. Okay, let's look at some other things related to that. So just like we said, 1 over 1 minus x is 1 plus x squared plus dot dot dot. Well, whatever we have in this position would end up would take the place of x. So if we see something like 1 minus cx, 1 over 1 minus cx, well, that's the same as 1 plus cx squared plus cx cubed plus cx to the fourth. All right, and if we expand each of those terms, then what we'll see is we get cx plus c squared x squared plus c cubed x cubed plus c to the fourth x to the fourth plus dot dot dot. And so what this means is that the coefficient of x to the k of 1 over 1 minus cx is going to be c to the k. Right? The coefficient of x to the fourth is equal to c to the fourth. So that's what's happening. That's what this sum looks like. A particular case of this is when c is equal to negative 1. So if we have 1 over 1 plus x, that's 1 over 1 minus negative x. And so c is equal to negative 1, and we see that the coefficient of x to the k of 1 over 1 plus x is equal to negative 1 to the k. Okay, so when you see a plus in the denominator, that's going to lead to coefficients that are negative 1. That's going to have an alternating power of negative 1 in the sum. There's also two other cases that we should just have in mind that we've already seen, and let's just talk about them. So 1 plus x to the n, and recognize that this is a polynomial, this is not an infinite series. So this is a polynomial, 1 plus x to the n, so this is 1 plus x times 1 plus x plus times dot 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 times 1 plus x. Well, in how many ways can we choose there to be k x's? Well, there's n different pieces, and we want to choose k of them to be x's and n minus k of them to be 1's. And so this is our binomial theorem. This is that when you see something that looks like 1 plus x to the n, you should think, oh, the coefficients are n choose k. Similarly, if you see something that looks like 1 over 1 minus x to the nth power, that is multi-chooses. So why should we expect multi-chooses in that case? Well, we can think of 1 over 1 minus x to the n as 1 over 1 minus x to the n. And each of the 1 over 1 minus x's, we've already said, is this infinite series 1 plus x squared plus dot dot dot. So each of them, all n of them, can be thought of that way. And so if we're thinking we want there to be x to the k as a product of these pieces, well, we're choosing some x to the I1 here, choosing some x to the I2 here, some x to the In here, where the sum of the i's is equal to k. So in other words, this really is the multi-choose. We've got some number of x's that we're choosing from here, some number of x's that we're choosing from here, some number of x's that we're choosing from here, and we can have as many as we want from each of those factors. And so when we take the product of those and equal to x to the k, in how many ways can we get k things when we have a product of n different pieces? Well, that's n multi-choose k. This gives us a formula for the answer on the previous page. When we had 1 over 1 minus x squared, well, if we look at what that is in using this formula that we just came up with, what we'll see is that this is going to be that the coefficient of x to the k in this is going to be equal to, well, in this case, n is equal to 2, so we get 2 multi-choose k. Well, 2 multi-choose k is equal to k plus 2 minus 1 choose k, which is equal to k plus 1 choose k, which is equal to k plus 1. Okay, and so what we have directly found is we've directly found that the coefficient of x to the k, or of our generating function, which is the number of ways to create a fruit basket with those constraints on the previous page, is going to be equal to k plus 1. And so we calculated that directly using this understanding that 1 over 1 minus x to the n should be thought of as a multi-choose. So let's use these techniques to do some examples. Let's find the coefficient of x to the 9th in 1 over 1 minus 4x to the 12th power. Okay, so when we see 1 over 1 minus 4x to the 12th power, then we should think this looks like 1 over 1 minus maybe y to the 12th power. Now 1 over 1 minus y to the 12th power, we can write that from the previous page as the sum from k equals 0 to infinity of 12 multi-choose k, y to the k. Okay, so now if we replace this y by 4x, we see this is equal to the sum k equals 0 to infinity of 12 multi-choose k times 4 to the k y x to the k. Actually, let's see. 4 to the k x to the k. And so then the coefficient of x to the 9th here, we can actually just read off here. What is the coefficient when k is equal to 9? It's 12 multi-choose 9 times 4 to the 9th. So that would be if x, remember, we're thinking of x to the 9th as objects of size 9. So how many objects of size 9 are there with this generating function? Well, there are 12 multi-choose 9 times 4 to the 9th. All right, let's think about this. Let's say we had something that looks like x to the b times some other polynomial. So we had, for example, x to the 10th over 1 minus x. What's the coefficient of x to the k of that? Well, let's think about what happens here. X to the 10 over 1 minus x. Well, we have this x to the 10. Let's factor it out. And we know that 1 over 1 minus x is 1 plus x squared plus dot 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 off to infinity. So now x to the k of this, if we expand this, what we actually get is x to the 10 plus x to the 11th plus x to the 12th plus dot dot dot. We can see that all of these all the exponents have been shifted by a factor of 10. And so if we're looking for maybe x to the 15th of this, it's kind of like we shifted 10 units one way, and then we want to shift now 10 units back. So in other words, what we would say is, oh, well, this is going to be x to the k minus 10 of 1 plus x squared plus dot dot dot. Or in other words, what we're seeing here is that x to the k of something that looks like x to the b times b of x is going to be equal to x to the k minus b. So the coefficient of x to the k minus b of x. So if we have a power of x that we can extract, that we can factor out of our generating function, then we just reduce the coefficient that we're looking for accordingly. So here's an example. Let's say you wanted the coefficient of x to the 10th in this expression. Well, let's break it down into two different things that we're looking for. X to the 10th times x to the 4th over 1 minus 2x plus x to the 7th, x to the 10th times x to the 7th over 1 plus x. So the coefficient of the whole sum is the sum of the coefficients of the different terms. When we see x to the 10, we want the coefficient of x to the 10th, but we have an x to the 4th that we can factor out. We can write this as x to the 10 minus 4, or x to the 6th, times 1, the coefficient of x to the 6th in 1 over 1 minus 2x. And here we want the coefficient of x to the 10th in something where we can bring out a factor of x to the 7th. So we can write this as x to the 10 minus 7, or x to the 3, times 1 over 1 plus x. Oops, I'm noticing that this is 1 plus 2x and not 1 minus 2x. Sorry about that. So now we have some coefficients that we can extract directly. So when we see 1 over 1 plus 2x, well, that's telling us that the coefficient of x to the 6th there is going to be negative 2 to the 6th power. And the coefficient of x cubed of 1 over 1 plus x is going to be negative 1 to the 3rd power. So in other words, we have 2 to the 6th, which is 64, minus negative 1 to the 3rd, so 64, minus 1, which is 63. So that's the coefficient of x to the 10th in this expression. All right. Another thing we might have to do is have to reindex our pieces. So when a clue that you might have to reindex your sums is if the subscript, the index of the sequence, does not match with the coefficient of x to the exponent of the x to the k term. So here we're seeing a k minus 1, and here we're seeing an x to the k. When you see something that looks like that, that's telling you that you need to do some sort of manipulation in order for you to match those up. So if we look at this, how can we take this expression and have the powers match up? The index of the sequence and the exponent of the x match up. Well, we look at this as a to the k minus 1 times k minus 1 times x. So we factor out an x. And if we factor out an x, then these things match up. And so what do we see here? Well, we see the sum k greater than or equal to 1. I'm going to bring this x outside the sum. And then I now have a k minus 1, x to the k minus 1. And if you look at this, we had k is greater than or equal to 1 down here. So we're going to do the substitution. Let's let L be equal to k minus 1, and then L plus 1 is equal to k. And so if we're looking at this, we have the sum, x times the sum for L plus 1 greater than or equal to 1 of a sub L, x to the L. And L plus 1 greater than or equal to 1 is the same thing as sum L greater than or equal to 0 of AL x to the L. And, I mean, you could put this back as K if you feel more comfortable with K, but this sum is just the same thing as our generating function a of x. So this is x times a of x. All right, so what we're seeing here is if you have something that looks like this, then that's the same thing as x times a of x. Similarly, we may look at this and we may say, we want to be able to write this. So, I mean, what I'm using here is I'm using that, I have it up here. A of x looks like this. What we're seeing here is that we're off by 1 power of x. So let's rewrite this as sum k greater than or equal to 0 of a sub k plus 1 x to the k plus 1 divided by x. Or in other words, we have 1 over 1 minus x times the sum k greater than or equal to 0 of a sub k plus 1 x to the k plus 1. Now if you look at what this sum is, this is the sum, let's put this up here, a1 x to the 1 plus a2 x squared plus a3 x to the third, etc. And you can see that what's missing is the a0 term, a0 x to the 0. So we know that a of x is equal to this whole sum, but what's in this sum is just everything after this term. And so bringing this to the other side, we get a of x is equal to, a of x minus a0 x to the 0 is equal to this sum, a1 x to the 1 plus a2 x squared plus a3 x cubed. So this expression would be plugged in here. And so our final answer here would be, this is equal to 1 over 1 minus x, 1 over x times a of x minus a0. Right, 8x to the 0 is equal to 1, so we can rewrite this sum in this way. Practice. Practice. All right, so now let's do an example. Talking about practice. Find the compact form of the sum for k greater than or equal to 2 of this. All right, so we should look at this and we should see that x to the k and something to the k minus 2 don't match. We need to have those exponents match. We also see that this sum is k greater than or equal to 2. So that's telling me that I see something that looks like k greater than or equal to 2. I think I'm going to use a substitution, and I'll think k minus 2 is equal to L. So if k is greater than or equal to 2, then k minus 2 is greater than or equal to 0. So L is greater than or equal to 0. So let's rewrite this as the sum L greater than or equal to 0, negative 3 to the L, times x to the, well, k is equal to L plus 2, x to the L plus 2. Now what I'll do is I'll factor out 2 powers of x, and I get x squared, sum L greater than or equal to 0 of negative 3 to the L, x to the L, which this is just, so this is x squared times 1 over 1 plus 3x. And so then this would be the compact form of your expression. All right, let's stop there for now. I will do a little bit more to talk about, and I'll do that in a subsequent video. Talk to you soon. Bye.